All right, welcome everybody. So in the last class, I was talking about programming in MapReduce, and there we had not looked at actual programming language. Rather, we were interested in pseudocode or algorithm. So MapReduce programming is basically key value pair processing. So the input comes as key value pairs, and the output is also key value pairs. The map function and the reduce functions that programmers write have to basically always remember this key value paradigm, where the intermediate keys and values need to be produced, and that's how map reduce these two functions work in a distributed programming environment. Today the focus is on Spark, and some of you have already seen Spark before in other classes, but we can look at some programs, right? How to write programs in Spark. And the idea is that programming in Spark will let us do distributed memory programming on very large scale clusters. So the code that you write will be able to run on cloud computing environment and large scale computational clusters. And the benefit is that there is less coding effort, in order to do so. So when we have threaded programming, right, multi-threaded programming, the effort required is much high. So by doing parallel programming with Spark, the idea is that we'll be able to do the same processing with little amount of effort with respect to coding time. All right. So why Spark, right? So it is a successor of Hadoop MapReduce framework. So Hadoop MapReduce was already there, but it was slow. And Apache Spark promises to make this faster, right? So in some sense, Spark MapReduce will work with the file formats and the distributed file system environment that were there for Apache Hadoop. So Hadoop distributed file system, SDFS, that can act as an input for a Spark MapReduce program, and Amazon S3 and object store, cloud files, you can access them through your Apache Spark program. The efficiency that I was talking about comes from some design principles that were employed in Spark. So one thing that we'll learn is that Spark is very, very fast, up to 2 orders of magnitude faster. And why does that happen? That happens because it is able to do stuff in main memory rather than going to the storage system, which is like hard disk, right? So it will not go to hard disk because it has some design improvements where you can say the data should reside in main memory because main memory is fast, so you can persist the data in the storage tier where you want for performance benefits. So because of these reasons, caching can happen, and we know caching improves performance. The other benefit that Spark provides is general computation graphs. So this is basically, when you write map functions and reduce functions, and then there are other functions also that you could do, like filter functions. So all these functions, you can chain them up as computational graphs, and then the system can process these graphs and do some optimization so that some redundancy gets removed in code, in computation, and we get efficiency, right? So these design ideas make Spark faster. All right, now how do you run it? So in my next class, I'll show you an example of running it. This time I'll just go through some basics because we only have part of the lecture today and not the whole lecture, and also I am teaching in an online fashion today. So I have Spark installation codes. the basically the software stack. It's there in um, in Canvas modules for Spark for MapReduce, right? So you can download it, and next time you can see. You can run it on a multi-core machine. So the multi-core has some benefits, right? Some parallelization benefits. When your MapReduce program runs, it can take those benefits. It gets some speed benefit. You can run those on cloud computing environment or in your private clusters. It can be programmed in different languages. We will see examples in Python, right? But you can do in other languages also. Often when you choose a particular programming language, there may be performance differences. For example, Java and Scala, these are compiled languages. Python is interpreted. So compiled languages, you can get some performance benefit. Also, the number of lines of code also may vary, because we know that in Python you don't need to write a lot. The logic could be expressed in a succinct fashion. There is also an interactive cell, so you can start that cell. It's also called REPL, and then interact with Spark. So you can run nuggets of code and see what's the output are, and later you can deploy it also. So we'll look at some details about Spark, some sample programs, and sample programs like word count, page rank. Page rank is a code to rank the web pages. So for example, in Google search, all the pages that you get, like let's say you're searching for COVID and you get a bunch of hits, then which should be the rank 1 web page, which should be the rank 2. That's the page rank. Word count pseudocode we have already seen in MapReduce algorithm. We'll also see that in terms of a Python based Spark program. So you could write a standalone program, which basically is like a Python program with a main function. The other is in an interactive mode. It's like scripting language, right? You could do both of that. So let's go to the key idea. The key idea in Spark is the concept of getting fault tolerance via the concept called RDD, right? So what does RDD means? RDD is a data set, and since we are talking about parallelization, the framework lets you do parallel and distributed processing because the data set is distributed, right? If you have multiple compute nodes, multiple hard drives, data will be distributed. We say resilient because it can tolerate fault. So it's a fault tolerant distributed data set. So you can recreate it if you lose it. So that's the resilient. Okay. So the key idea is to work with distributed collections in the same way as you deal with local collections. Like local means a single machine where your code is running. Distributed collection means if you have let's say a list, that list is distributed among the compute nodes. For example, if you have 1,000,000 elements in a list and you have to process all the elements of a list, that list or a collection will be range partitioned or hash partitioned and distributed among multiple compute nodes. So the idea of RDD, first we know that things are spread, but also immutable. Immutable, the idea is that if you have a data structure, you cannot change it in place. So that idea is called immutable. So if you have to then do something, then you have to create a new type of collection. So that way, you started with A, you want some change, then create a new collection called B from A. So by doing that, you did not change A, rather you copied it and created a new collection, right? So that's why it's called immutable. So RDDs are immutable. Once you have the file in a disk, that's where you start, right? And then you apply a bunch of transformations, and the transformations are like map. So you remember map function of MapReduce. It's a user-defined function. And then filter is another function where you are interested to take a subset of the data in order to reduce the search space. So these transformations are applied in parallel because that's what MapReduce implementations like Spark will do. So they will chunk the data in parts, like I was talking about, the large file being partitioned into small chunks like 64 megabytes, and these are user defined. So that's why these functions can be applied in parallel. And fault tolerance, I talked about, if there is a failure, this data set, this resilient distributed data set will be recreated automatically, right? So fault tolerance. And I was also mentioning, that you can do caching. So not everything that you have computed has to go to the disk or the storage device, because you can cache it in RAM, because sometimes what happens is you reuse a particular data set multiple times. So if you are going through the data set multiple times, then rather than loading it multiple times from the slowest medium of access storage, you basically read it from main memory, and that's what you can do. You can control where the data should persist. Alright, now we come to the basic operations that Spark supports. So there are two basic operations. The first one is called transformations, and the second one is called actions. So some of the functions are transformations. For example, a map function, a filter function, and other functions like group by and join. This join is like a database join, where you're combining two tables. So these operations are called transformations. And the definition of transformation is that any change that happens lazily. So these are the operations that are called lazy operations. So for example, map will work on part of the data, and then it will produce another resilient distributed data set, right? Now this operation does not have to execute immediately. The system will remember that this has to be done, but it does not have to be done immediately. So that's why it's called lazy, because the transformation, for example, map or filter, can wait. So at some point, as you're going through the Spark program, user needs to know the answer, right? And that's where the actions come into picture. So when the user wants the result, then either it has to be visible in the screen, or it has to be written to the hard disk, right? External storage system. So whenever you want the result, that's where the actions are. For example, count. So what you would be counting. Typically, if you're searching for something, let's say COVID in your data set, then how many occurrences of COVID are there? So since this is an action, it will not happen lazily. The Spark program will make anything that is needed to give you the count, and it will run it. So that's why it's called action, right? So if count requires a filter to happen, then the filter will execute. So it will wait unless and until count has to use filter to produce the result. So one of the operation is lazy, for example, filter, but when you want the answer, it cannot be a lazy operation because the user wants the answer, right? So these are called actions. So collect is another function. It basically means get the data, get the answer from other threads, other tasks. Save to the file system. Here also you can't do that lazily, because the user has explicitly said we want to save, right? So RDD, and you want to save the resilient distributed data set, that will be an action. So in short, actions force the evaluation of the transformations required for the RDD to actually produce the output, right? So this is very important. All right, so we have seen transformations and we have seen actions. Now we have to see an example, right? Let's take a look at an example. So this example basically shows, how a Spark program gets executed. What are the different phases? So this example is called mining console logs. So suppose that there are log files in the system, and a programmer is interested to read these log files, and he's interested to filter some pattern from the log files. So how does that happen, right? So this picture shows that there is a driver program. This is like that will start the map functions and the reduce functions and other transformations and actions. So this is like main, and then you can see also workers. So workers are the compute nodes whose job is to run these transformations and actions. And you also see caching, because I was talking about this feature of Spark where you can cache a data set, cache an RDD, so that you can do computation in faster medium like DRAM rather than rather than the hard disk, right? And this picture also shows you blocks. So blocks, basically the data set is partitioned into blocks. For example, 64 megabyte blocks. Okay, so the user is interested to load the error messages from log into main memory. Then you have to search for some patterns. So the base RDD is created by reading something from distributed file system, Hadoop distributed file system. So you basically give a path, and based on the path you get the RDD, right? So this is the lines is an RDD. It's a collection of the data that is there in the log files. Now this lines is now used here. So you are running a filter transformation on this RDD, and you are interested to find out the lines in the log file that starts with error, right? Because what is a log file? Log file is documenting what is happening in the software as it is dealing with the data, reading the data, writing the data. So there are many lines of there are many sentences, many lines. So some of them starts with error. So that's where you're interested to only look at those. So in Python you have the concept of lambda functions. So lambda functions, you can write a function in succinct way without boilerplate that we see in programming languages like C and Java. So what this basically says, for each sentence, look for this pattern with error. That produces a new RDD, a transformed RDD, errors, and then errors is then used to do a map function. And the logic for the map function is that the sentence has many words, so just split the sentence into words, and the delimiter is tab. So it is assumed that you can look at the log file as having sentences like a table. So there are multiple columns, and these are tab delimited. So you split the sentences into words and then pick the second column. Okay, that's what this 2 is about. This is Python syntax, and the idea is that this particular column holds the error information, and that is, you can access that using messages RDD. And since messages would be used multiple times, you cache it. Okay, cache it to main memory. And now you're searching for some pattern. So the pattern could be looking for the lines that starts with error. What are the lines that have foo, and you want to count? And that is an action that basically means that it will make sure that the transformations like filter, map, these run, right? Otherwise, when the system is going through filter and map, they will run in a lazy fashion, in the sense that they don't have to run. It can wait, and the computational graph will be made. Like the system will remember what functions have to be invoked on which collections. The system will track that through a computational graph, but it will not run, right? It does not have to run, and the running will happen when the user's code that has an action executes. So that's the count. So count happens, then the system will then do the reading part, and then do the filter part, then do the map part and the cache part, and then count. The answer is returned. So the first time when this happens, searching for foo, it will be slower, but the next time it's already cached, it's in main memory, so the next filter, searching for bar, would be very fast. All right, so that's what this example shows. They had a comparison. They tried 1 terabyte data, and this program finished in 5 to 7 seconds, going through the log files, searching for patterns like foo, bar, looking at the error column. On the other hand, a system like Hadoop MapReduce that looks at the data from disk is slower. It takes longer time, right? 1/72, and that happens because this caching mechanism is not built into Hadoop MapReduce. It always goes to the disk to read the data, and a reading disk is very, very slow. So in the data center chapter, if you remember, the presenter was showing what's the difference between I think it was Amrit. What's the difference between reading something from main memory versus reading from disk? So that's the difference. All right, and now let's take a look at fault tolerance, because we know Hadoop MapReduce provided fault tolerance. Spark MapReduce also has fault tolerance built in, and the idea is based on lineage. So the idea of lineage is like we have grandfather has a son, and then a son, grandson, right? So this is the lineage, how things have come. So you can pick a person and ask, what is your lineage? Then the person will say, my father was X, my grandfather was Y, my great 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 grandfather was alpha, beta, something like that. So when you have resilient distributed data sets, when you have RDDs, these RDDs will also remember their lineage. So start with a file and then do some transformation and then do next transformation. So a graph is created. In this example, the graph is actually a line, right? But a line is also a graph. You have directed edges. So the lineage information is mapped RDD knows the father, filtered RDD, mapped RDD also knows the grandfather, Hadoop RDD. So if something happens, you lose mapped RDD, then mapped RDD could be recreated because the system knows the lineage, and it can recreate from the RDD that is available. In this case, if the file has been replicated multiple times, if you have lost 2 copies, the third copy is maybe there, and then you can recreate mapped RDD, taking advantage of the filter, or not the filter, sorry, the lineage information. So this is the example. You start with the base RDD, which is coming from a file, apply this filter, and then apply this map, right? So this picture corresponds to this line of code. So for each line of code, the Spark system will make a graph, adding edges, adding nodes, and then you have a computational graph. So system has this memory dedicated because the fault tolerance has to be implemented. All right. This is another example of a lineage graph. So on the left side, I'm showing you transformations. They're basically 3 transformations. And on the right side, I'm showing what kind of graph does Spark create as a lineage graph, right? So you have a filter function in line number 1, you're searching for error. On line number 2, you're searching for warning, and then you're doing union of the 2 RDDs that you get in the previous 2 lines, right? So union means kind of combination, right? So sets, union of 2 sets, remember that. And the corresponding graph, a lineage graph, is input RDD, the filter happened, you got a new RDD, errors, and then you had warnings RDD because of second filter, and then the union happened because of these 2. So let's say this lineage graph is there and bad lines RDD got lost, right? The machine which were responsible for storing this RDD lost the data. Then the system will look at the lineage graph and will make sure errors RDDs are created, and once errors RDD and warnings RDD are computed, then the union could be done to get the combined RDD, right? That's how you recover and tolerate faults. All right, so that's the concept. We talked about languages. So I think Python is the most popular to do Spark programming. In the beginning, Java support was there, but at that time when Spark was developed, Java still did not have these lambda functions, so it was laborious to program using Java. The performance-wise, Java Scala is faster. So Scala has a JVM runtime. The language is very difficult to master, but it is a Java-based language. But the way to program is very different. So the runtime similarities are there, but the languages are very different, and it's a functional language. That's why it's very different. So these compiled languages, they are faster. But if you are using NumPy related stuff, then Python Spark will work well as well, because NumPy is very well optimized. All right, so I was talking about you can run Spark in different modes, right? So you can run it on your laptop. So if your laptop has a Mac, Apple Mac, that operating system, or Linux, it's very easy to install. So it can run on a single thread. You can specify that you want to run it on 2 threads by first writing master equals to local 2, because 2 threads, and then /spark shell. This is what you do to start Spark in an interactive fashion. So this is what will start the REPL. You also have other options, like you have a dedicated cluster, and you know where the files are. Then you specify the path so that you could use a standalone cluster, and then /spark shell. So you can use it in different modes: single threaded, multi-threaded. All right, so in most of the languages, implementations, like whether you choose Scala, Java, or Python, there's a built-in class called Spark context. So if you use Spark context, then you'll be able to use many pre-built mechanisms that are there in Spark, right? When you're dealing with Spark shell, you can use sc. These 2 letters basically means that Spark context is already available. I'll show you both kinds of programs, standalone programs, as well as scripting, right? Script-like programs. All right, now let's take a look at a few examples. So we have seen actions, transformations, fault tolerance. So we have seen few stuff, but now we can take a look at how does the program look like, because so far we looked at small pieces of code, but not full code. So let's take a look at some examples. So how do you create a RDD? So first example was read a text file, and that's how you start with an RDD. The other is use parallelize. So if you have a collection, you can either pass the reference to the collection. In this example, it shows that you want to parallelize 1, 2, 3. That basically means that this array will be range partition or hash partition among threads, so that you have multiple tasks and you could do some parallelization. And this is just an example, because if you have 3 numbers, you don't need parallelization, right? But the idea is, if you have a long list, you can create an RDD using parallelize. This you have already seen, how you read a data, so a text file and the path. Here you have a directory and a path, and here you have the path is in the distributed file system, and you can specify the type of the files also. Now let's take a look at a few transformations. So first you create an RDD by parallelize, and then you run a map function. So what does this map function say? The map function says that if you have some input like 1, 2, 3, you want to do for each input x, you want to square it, x times x. So 1 becomes 1 because 1 squared is 1, then 2 becomes 4, and then 3 becomes 9, right? So this is how you write a lambda function in Python and show the logic that for each input of the collection nums, you want to square the number, and that's what the output should be, right? Output squares. Now if you're now you can use filter function, and the filter function is, well, I have an RDD that has 149 and that's encapsulated in squares. How do I filter a pattern? Like, I'm only interested to see what are the even numbers. So your lambda function can use something like x modulo 2, where you're saying I want to filter those numbers that are evenly divisible by 2, and that's the definition of an even number, right? So that's the filter, and that the answer would be stored in a new RDD. It's called even, and you don't have to specify the type of these RDD. The system is smart enough to infer the type. Now let's take a look at flat map, because we have already seen map. So flat map is a bit different from map. The definition of flat map is map produces multiple elements. It can produce a single element, but a map can also produce multiple elements. So if you have output of multiple maps, you can serialize it, you can flatten the output, and that's called flat map. So basically it means combining multiple lists into single list. That's what flat map is. So what's the logic that is being provided in this example? The logic is basically, there are lots of inputs in nums, and that is 1, 2, 3, and for each of these input values in nums RDD, you want to apply this lambda function. And the lambda function says that you want to take an input and then make it go through the range function, and the range function is defined as if you have range 2, range of 0 comma 2, then the output is 0 1, because if you have x, the output goes from 0 1 all the way till x minus 1, so it just leaves the last x, right? So that's why x minus 1. All right, so if you have 1, that gives you what does it give you? So it starts from 0, right? So it has to have a 0, then that's it, because it cannot have a 1. Then let's go to 2. What will the range function produce for 2? It will produce 0 1, right? Because it cannot have 2, x minus 1. And then you go to 3, and then what is the output of the map function? 0 1 2, right? So 0 to x basically means 0 1 x dot 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 x minus 1. And flat map, basically, there are 3 outputs of this lambda function, because there are 3 inputs. So the lambda function has been applied to each of these elements, and flat maps is basically flattening the output of each of these maps. That's why it's called flat map. All right, we'll stop here today. We'll carry on with it. We'll continue with it in the next class. All right, thank you. We'll stop here now.